Well, hello. Today, finally, we're doing some real trigonometry. Up till now, we've looked a lot at right triangles and the relationships, but this tangent here is the first real trig function. And if you're not familiar with the expression trig, I hope you get used to it. It's just short for trigonometry. Nobody likes to say trigonometry, trigonometry, trigonometry over and over and over again. So most everyone just says trig. And in keeping with being lazy, no one writes out tangent. For instance, the tangent is a trigonometric function. For an angle, it has a value. And in fact, it only has values for angles. The tangent of 3 inches does not exist. The tangent of anything but an angle doesn't exist. It only applies to angles, and it's normally written this way. Tan. We just write like this. It equals something. We don't know what yet. Well, this ratio is defined to be the opposite over the adjacent, which in this case, of course, would be BC over AC. But opposite over adjacent is the actual definition. It's usually written this way. To help you remember it. Opposite over adjacent. Now this for this angle. Suppose I wanted this angle here. Call this angle beta. Well, opposite over adjacent. Well, looks to me like it's just the reverse of this. So, the tangent of beta is just AC over BC. In other words, I'll write it over here. The two angles in a right triangle, forget the right angle for now. Just these two. Tangent of alpha equals 1 over tangent of beta. Now, when I draw the right triangle this way, if I were to put, say, some axes in here, let's say that's suppose that's a y-axis, and that's an x-axis, what would BC over AC be? Remember? Well, this is kind of like the rise, isn't it? And this is like the run. So this BC over AC would be the rise over the run. And that would just be the slope of this line. This line that's actually going through the origin here. And in fact, that is the case. The tangent of alpha is the same as the slope of this line here. It helps that I put the vertex right at the origin. The tangent of beta would not be the slope of this line. This line here. But this one, yeah, it'll be, and anytime if you can lie it down so that it's set up, your tangent becomes the rise over the run. That's all you have to do is orient your right triangle so that your tangent becomes the rise over the run. If you do that, for instance, I could lay it down so that BC was down here, and AC was, wow. And this looks a little bit better, I guess. If I were to lay this down so that BC is down here, and I kind of change the scale, things are getting a little crowded, then the tangent of beta would be the slope of this line here. Here's beta over here. Just had to lie this down and then flip it over. Because if we're looking at this angle, now the opposite is AC and the adjacent is BC. Get it? It's a fairly simple idea, but it gets used a whole bunch. And you just have to remember opposite over adjacent. There's a mnemonic we can use to remember these, but I'll have to give it to you when we learn the other two major trig functions. There are two more coming up in future chapters, at which point I can give you a real simple mnemonic that will help you remember which is which. For now, just try to remember, or maybe write it on the palm of your hand or something, that tangent is always opposite over adjacent. And by opposite, we're referring to whichever angle you're taking the tangent of. If you're looking at this angle, the opposite is AC. If you're looking at this angle, the opposite is BC. So this is a really fairly simple concept. We've just given a name to a ratio. We've used lots of ratios before. We didn't usually give names to them, but this particular ratio has a name. Just as the rise over the run, that's a ratio, and we called it the slope. Well, here's another ratio, and it has a name, and the name is tangent. And I can give you another rule. That's maybe the fun thing about trigonometry. You can come up with all kinds of relationships. Alpha and beta on this right triangle here have this relationship. They have another relationship, don't they? I'm going to put it up here. From the triangle, this triangle Sum Theorem, all the angles have to add up to 180, but this one we know is 90. That means these two have to add up to 90. So, what we have here is that we could substitute (90 minus alpha) for beta. In other words, right here, we could write the tangent of alpha is equal to the tangent of 90 minus beta. And down here we can do the same thing, because they're complementary. So the tangent of alpha is the same as the tangent of 90 minus beta, which is also the same as 1 over the tangent of beta, which I wrote over here. Let's see. So here's another little fact. We take 90 minus beta, that's the same as the tangent of alpha, and of course vice versa. The tangent of 90 minus alpha would be the same as the tangent of beta, because 90 minus alpha is beta. But what does that mean? Tangent of beta is 1 over the tangent of alpha, so we can go from here to here and have that tangent of 90 minus alpha is the same as the tangent of, the tangent of 90 minus alpha is 1 over the tangent of alpha. All these relationships are very standard trig relationships. Learning them, aside from being a pain in the neck, is very useful, because these identities are going to come in over and over and over later on when you study trigonometry. You're going to use these a lot, especially the relationship between alpha and say alpha and 90 minus alpha, or beta and 90 minus beta. Very strong relationship there, and you will use these frequently in solving problems in trigonometry for sure. And when you go on in mathematics, you will use these. These are called identities, by the way. Trig identities. They're very important. Your calculators have some of these. Otherwise, I actually have an old book at home. It's I forget where I found it. It's got a really, really old publication date. It's like something people would have used like right after World War II. It's pretty cool. I like old historical type math stuff, and it has a table of trig identities. When I say table, we're talking about pages and pages and pages of trigonometric identities. It's huge. Well, that just leaves me, I think, with one question. You probably have heard the word tangent before. Tangent, to most people, would mean a line that touches a circle in just one place. I'm not sure if they mention it in Algebra 1. I don't think they do. But somewhere along the line, somebody has probably told you what a tangent is, or maybe a tangent line, or it just brushes a circle at one point. If it's not a tangent line, something like this here, that's not a tangent line. It intersects the circle at 2 points. And in fact, it's funny because there's exactly one line that will touch the circle at one point. If you tilt this line at all if you rotate it, in other words, either clockwise or counterclockwise, the slightest fraction of a degree, you won't have a tangent line anymore. You'll have something that intersects the circle at 2 points. The 2 points might be like right next to each other, so close that you can't even see, but the fact is there is only one line which will touch the circle at only 1 point for a given point. I mean, the tangent line over here at this point is not going to be the same as this tangent line, but for any given point on the circle, there is only one line which would be tangent at that point. You're probably already familiar with that, at least vaguely. You may not have gotten all that rigor with the definition. Maybe your older brother or parents or somebody told you what a tangent was. Well, why in the world would we call something which is just the ratio of the two legs of a triangle and give it the same name as a line which brushes a circle at one point? What sense does that make? I mean, what kind of mushrooms were these people eating when they came up with this? It's not quite as crazy as you might think, and I'm only mentioning it because as a student, if it was me, I kind of wonder, why the heck have we got two completely different things with the same name? After all, mathematics is a language, but it's not an organic language. It's not like somebody came from Africa and started doing mathematics with somebody from Norway, and they had two different words and just sort of put them together, so one guy's using the African word for something and the other one's using the Norwegian word. No, it doesn't usually work that way in mathematics. So how the heck did this happen? Well, first, we'll have to take a walk back to ancient Greece. Now, I'm not talking about McDonald's. That would be rancid Greece. We're talking ancient Greece. Well, first thing you might have to keep in mind if you're going to try to crawl into the brain of an ancient Greek is they had no algebra. They had no symbolic logic. For instance, if Euclid was going to say something like this, which we call the additive property of equality, if A equals B, then A plus C equals B plus C. If you showed that to Euclid, he wouldn't know what you were talking about. On the other hand, if you were to say to him, if equals be added to equals, the result yields equals, that would make perfect sense to him. That would be a postulate that he was familiar with. This right here, this would mean nothing to him. They had no symbolic logic. They had no algebra. They had addition. They had the division, multiplication, and all that. They didn't have variables that they could insert. They tended to work with things that they thought were concrete, like lengths of lines. This AC here is a very concrete thing. You don't have to think of it as a variable if you don't want to. So, if they didn't do this, and they didn't have algebra, how would they look at things like this? How would they compute them? Well, glad you asked. Let's take a look. Now here we have some stuff that I'll have to explain. And keep in mind, the Greeks worked with concrete things like line segments which had definite lengths. I mean, if you talk to a Greek about the square root of -2, he would just say you were crazy. It wouldn't exist for him. Okay, so we've got this circle here. Remember this triangle from a previous section where we found all these relationships? Once we dropped an altitude into this right triangle, it separated the hypotenuse into segments, which we could say that, for instance, CD over AD was the same as DB over CD. Now, the tangent, say for alpha, right here, put that in there, say that's alpha. So our tangent function would yield, in this case, CD over AD. This is some quotient. And as this line comes up here, and if you're not familiar with it, this happens to be called a radius. You'll learn that in a couple of chapters. It's not real important right now. I think everybody knows, probably, that there's a line from the center of the circle to the circumference. And it's called a radius. No big deal. This circle has a radius equal to 1. I just drew it that way. They don't always have a radius equal to 1, but you can always draw it that way if you want to. That means that AC has a length equal to 1. And what we're going to show is a relationship between the tangent, the real tangent, the one most people would think of as a tangent, if you interrogated some random person at a bus stop and said, what's a tangent? He'd probably draw a circle with this little line just touching it. It's very unlikely he would draw a right triangle and say that and say that it's the ratio of the opposite over the adjacent. He might. But most people think of this as the tangent. What's the relationship between this and this tangent here? Well, this is weird. This is, I drew the line through the B, but that's supposed to be a B right there. Let's see if it can. No, that's no good. Yeah, let's put the B next to it, or yeah, put it down here, I guess. This is B, okay? Right here where this line touches. So this is CB. And we've got a whole bunch of relationships up here for our triangle. The odd thing is the length of the line from this point, which is the point where we're computing the tangent. It's also the point that is the trigonometric tangent function. Or in this case, we could even call it the slope, because that's what it turns out to be, the rise over the run. That ratio turns out to be exactly the same as the length of the line from the tangent, from the point of tangency to the point where it intersects the x-axis. Sounds kind of weird, doesn't it? Let me write it down. See if it helps you understand what it is I'm trying to say here. CD over AD, which is our tangent for alpha, it would, in this case with this line, it would also be the slope, is equal to CB, the length of this line here. I don't know about you, but that seems kind of bizarre to me. I mean, pick another line. Suppose we had a tangent here. That would take off and intersect way out here. Or if we had one way up here and it could intersect way, way out here, it would still be true that the distance from the intersection point to the point of tangency was exactly the same as the ratio of the opposite over the adjacent. And that would show some connection between our tangent function and what we normally call a tangent, wouldn't it? Because the length along the tangent line is exactly the same as the value of opposite over adjacent. You don't think that's true, do you? Well, I don't blame you. Seemed pretty bizarre to me, too. But there's a way to show that it works, and it's actually not nearly as tough as you might think. First thing I'm going to do, and you'll see this in proofs sometimes, remember you always do whatever makes it easiest for you. In this case, I'm going to start with the value of the tangent, and I'm going to show that it's equal to the length of this line here. Yeah, right, you'll believe it when you see it. Well, okay, just hang on here. Now I'm going to do something strange. I'm going to square it. Why? Well, I'm going to come clean. I did this before, and I know it works better this way. That's the only reason. Don't look at it and think, gee, I wouldn't have thought of that. Yeah, given time, after a few false starts and a few mistakes, you probably would think of it. As far as it being the first thing you would do, no, hardly anybody would do that right off the bat. It doesn't make any sense. But it turns out to lead to a fairly direct conclusion and shows that this CD over AD is the same as this little length here. First thing we can do is rewrite this. What would CD squared be? Well, we have a relationship over here. If we cross multiply, CD squared will be 80 times BD, right? But we can substitute and write in BD times AD. And that'll be over AD squared. Well, I think I see a cancellation going on here, right? So we can now set this equal to BD, gee whiz. Let's see if I can draw a D. There we go, sort of, over AD. Now here comes another tricky part. I drew this with a radius of 1. In mathematics, that's called a unit circle. It's used a lot. If you don't have a unit circle, you better get yourself one. You're going to need it if you go on to do any more mathematics. And since this is a unit circle, this hypotenuse here, it's equal to 1. That's what it means to be a unit circle. And I'm just giving you the word because you'll run into it later. Unit circle isn't a phrase that you need to be familiar with right now, or probably even in this class. That means that over here we have AB over AC. Well, we can replace AC with 1 equals AC over AD. So AB equals 1 over AD. But we have a 1 over AD right here, don't we? So now we can make another substitution and write that this ratio is actually the product of AB and AD. Pardon me, that's that's supposed to be a BD over here somewhere. There's AB, and this part, yeah, sorry, I wrote that wrong. This is BD here. I'm not used to doing things like a Greek. I like symbolic logic. I like variables. They make life much simpler. Anyway, we've now gone from CD over AD, quantity squared, to this. Made with a substitution, of course, performed a cancellation between the ADs and got to here. Now we can substitute our 1 over AD with an AB and get AB times BD, but I think there's something over here with an AD times DB, like right in the middle here. AB, well, BD, DB, same thing. I just wrote it backwards. Or maybe they wrote it backwards. Who knows? CB squared would be AB times DB. Well, that's what we have here, AB, BD. So this equals CB squared. Oh, wait a minute. We just went from CD over AD squared to CB squared. that means that we pretty much have this equation here, don't we? I could square both sides, or we're not working with negative numbers in this case. These are all positive numbers because they're lengths of segments. So we can say that the square roots are equal, which means that CD over AC equals CB. Which is exactly what we were trying to show. The ratio of this over this, which is the tangent function, is exactly the same as the length along the tangent line from the point of tangency to the point where the tangent intersects the x-axis. And that means there is definitely a relationship between the tangent line and the tangent function, especially if you're a Greek who doesn't use symbolic logic or algebra. This relationship would be important to you. When I said Greek, I meant ancient Greek. Modern Greeks, they're the same as me and you. The Greeks from 2,500 years ago, they were different. Modern Greeks, they use algebra just fine. So now you might be able to believe that the word for this function, which is the opposite over the adjacent, the word tangent was just not pulled out of a hat. It just didn't pop up by accident. And there actually is a relationship, even though it's not at all obvious. At least not to modern people. One more thing I should probably mention about tangents. For the most part, we don't spend a whole lot of time measuring the opposite side and the adjacent side, and then computing the ratio. In fact, you probably won't spend any time doing that. What you will do, mostly, especially in more math classes, is use your calculator. I think I mentioned before, back in the Dark Ages, they actually had tables, printed tables, which you would just go look up. If you want to know what the tangent of 30 degrees was, you would look up 30 degrees on your tangent table and read it. And it would be some decimal point with about 6 or 7 numbers after it. Well, today we don't have to do that. We can use a calculator. I thought I ought to just show you at least, how that works. For instance, first make sure your calculator is set to degrees. Here it says degrees right here. There's also something called radians, which we'll worry about later. For now, just make sure that you're set in degrees. So say I wanted the tangent of 45 degrees. I punch in 45 and then hit tangent and I get 1. And that actually makes sense. If you're not sure, I can show you why that works. Hang on. Why would this be right? Well, if this is 45 degrees, we draw our hypotenuse out here, that would be the actual line. And here's our y, or opposite side. Well, we have a right triangle here. And in fact, if this is 45 degrees and this is 90, this must be 45. Well, what does that tell us? Remember from a section or two ago, an isosceles right triangle has two 45-degree angles here, and conversely, two 45-degree angles means you have an isosceles triangle, and there's no other choices for this angle here other than 45, which means this side, this opposite side, is exactly equal to the adjacent side. So this divided by this gives you 1. See? Makes perfect sense. And you could try some others, like, well, you can fool around. Try 60 degrees, take the tangent, get a big number. Well, actually 1.7 isn't that big, but calculators do that. 1.7 is probably good enough. What happens if you punch in 90? Ooh, yeah, can't do that. Why would it be invalid? That's one way to put it. Well, rise over the run. If you're at 90 degrees, you're straight up. Remember, we don't have a slope for straight up and down lines. Well, for a tangent, 90 degrees means that probably the best way to put it would be that as you rotate this line over this way, this gets smaller and smaller and smaller, doesn't it? Because this line just keeps moving over. As you rotate this up until it coincides with this, there is no more right triangle, because this length right here doesn't even exist anymore. After all, we have a point here where this line, in this case hypotenuse, is connected right here to this side, the vertex. Now, if I keep rotating this up, this part just keeps moving in farther and farther until it coincides with this line, and pretty soon we just got this line on top of this line. This line is on top of this line, and the adjacent side has an angle of 0, and that's, the adjacent side has a length of 0. And if we put opposite over adjacent, which is opposite over 0, that can't work, and that's why it says invalid input. Now if we put in 0, that should work. Yes, because the tangent of 0 is in fact 0. 0 degrees means that this thing is just lying down flat here. So we have the opposite side has height 0. Gee, why'd you go away? There we go. The opposite side has height 0. And it doesn't matter what the length of x is. 0 over anything is still just 0. But 0 in the numerator is defined, and of course it is 0. Did I say numerator? I meant to. 0 in the numerator is fine. 0 in the denominator? No. Can't do that. Won't work. So let's work some problems using the tangent ratio and see how it works out. What have we got here? Oh, and these are a couple of problems where looks like postal employees have now taken up trigonometry. Let's see how they do. Tangent of d equals 18 over 82. Well, let's see here. Here's d. Opposite. Remember, the tangent is opposite. Rewrite it. Over adjacent. Whoa. Opposite over adjacent. 80 over 18 would be the tangent here. So, there's the correction. I'm not sure what they mean by not possible, but we'll see. Tangent of 55 degrees. Well, there's 55. There's the opposite leg. So normally this would make perfect sense, wouldn't it? 55, opposite, there's adjacent. I only see one problem though. 30 and 55, neither one of these are right angles. And if we add them up, we get 85. But these two have to add up to 90 for a right triangle, because we have a 90-degree angle here. If these two add up to 85, that means this is a 95-degree angle. That means this isn't a right triangle. So when they wrote not possible, well, it is possible to correct the error. The error is you're applying trigonometry to a triangle that is not a right triangle, or at least you're applying the right triangle functions to a triangle that is not a right triangle. Trigonometry can definitely be applied to other triangles, but it's a little more complicated. It's not just the opposite over the adjacent anymore. However, if we're going to do it in terms of ratios of sides, it has to be a right triangle. And this isn't. So that's the problem. You have to apply right triangle functions to right triangles. Here they want to know which one of these expressions could be used to find the value of x. And in each one of these, we're assuming that we have some way of computing the tangent of these angles. And I just showed you the usual way of doing it is to pull out your calculator and press the TAN button. So let's write out what this is in terms of tangents. This is the angle here we're concerned about. We want opposite over adjacent. So we have the tangent of 40 degrees equals 20 over x. Now we're solving for x, of course, so what we would write here is x equals 20 over tangent of 40. This is just some algebraic rearrangement to end up with this, and it looks just like this one here, doesn't it? Well, the answer is, of course, C. All you had to do was just recognize that the tangent is opposite over adjacent, and you pretty much had the whole thing solved. And here's another fairly simple application of the tangent ratio. What is the value of x? Well, remember the tangent of this angle is opposite over adjacent. So that's x over 12. And that's equal to the tangent of 32 degrees. Well, that would give us that x is equal to 12 times the tangent of 32 degrees. Now, what we have to do is punch in 32 and take the tangent. Whoa. Let's just call that 0.63. Or, yeah, let's stick with 0.63. I think that's good enough. Times 12. It looks like about 7.2 or something like that. Try the calculator again. And when I do this, I get 7.56. But suppose we use the calculator the way you normally would. I just wrote it out this way to demonstrate exactly what we were doing. I think that if this calculator works that way, I'm not too sure about these online calculators. Let's see here. We had 32 degrees, right? So we just punch in 32 and then take the tangent. Now if I hit multiply, hopefully it'll just take that and multiply it by the next number I put in. That's the way my calculator works. Yes, okay, good deal. And that's 12. 7.49. Well, okay. See what happens when you round off? That's the only thing I did different. I rounded that to 0.63. And that changed it. So this would round off to 7.6, and the other way, well, which way should I put it out? The other way would round off to 7.5. So I would say 7.6 or 7.5, either one would be right. That one's here. So when I say either one would be right, I mean reasonably correct within for this problem. I think that if you did it this way and wrote out 7.56, I expect your instructor would give you credit for it. But ask him or her. This is slightly more correct. I didn't round anything off, as you noticed when I... Is it still visible? Yeah. And here's the long one too, which I did round off. It's a little silly. Who needs 15 numbers after the decimal point? Well, here's one that'll take about half a lifetime. It's probably not that bad. We'll see. There's a whole bunch of conditions here. The maximum incline is 5 degrees, and I think we're going to assume that they're using the maximum. And the maximum rise is 30 inches. After that, you'll have to produce a flat landing, which is looks like 5 feet long, and then produce and then another ramp. In other words, you can't just go from here all the way up at 5-degree angle and so you're going up 6 feet. You can't do it that way. I assume it's a safety feature, because when you figure out what the length of this is, if you had one of these that went up 6 feet and somebody lost control of their wheelchair up here near the 6-foot point, they'd pick up an awful lot of speed rolling down that distance, whereas this ramp is quite a bit smaller. Suppose the ramp was like, suppose it took 30 feet to get up. Well, gee whiz, I don't think I'd want to be out of control in a wheelchair rolling 30 feet down a ramp. Actually, this kind of sounds like fun if you wore a helmet. Anyway, what they want to know, given this situation, first, now they're asking for the length in feet, and they give us the dimensions in inches. Let's go ahead and work it out in inches. We can convert later. What the heck? This base here, remember, tangent is opposite over adjacent. And we're going to call that base, let's call it B1. In that case, the tangent of 5 degrees equals 30 over B1, or B1 equals 30 over the tangent of 5 degrees, which is going to be kind of a big number because the tangent of 5 degrees is a small number. We divide by a tiny number, we get, everything gets bigger, doesn't it? So let's see how this works out. We have 30 divide by, oops, yeah, let's see if I can do it this way. Okay, it's pretty easy once you get the online calculators worked out. Let's suppose we want the tangent of 5 degrees. That's easy. Now let's put that in memory so we can use it. Okay. Now what we do is punch in 30, divide, and bring back. That's not what we had before. Now try that again. We put tangent of 5 in memory, reclaim memory. Now we've reclaimed the tangent that we already computed and get 342.9. And a whole bunch of stuff after that. That's inches. So now we have to divide by 12. 28.57, he said round to the nearest foot, so that'll give us 29 for B1, approximately. Okay, that was fun. What about this one? The doorway is 7.5 feet above ground. What's the least number of ramps? Well, for every 30 inches, we need 1 ramp. So we just have to figure out how many 30-inch segments are in 7.5 feet. Well, first we got to convert to inches. So we got 12 times 7.5 feet. That's how many inches we'll have. So we get that 90 is the total number of vertical inches. That's the total rise we have to accomplish with all these ramps. Well, at 30 inches apiece, all we have to do is divide 90 by 30 and get that we need 3 ramps. Well, with 3 ramps, that'll produce 2 landings in between, right? We don't need a landing at the last ramp, and we don't need one in front of the first ramp. We only have to put landings in between. So if we got 3 ramps, there will be 2 landings. One after the first one and one after the second ramp. And that'll be it. So it's 3 ramps, 2 landings, maybe there's another reason for this landing. If you did lose control of a wheelchair here and got going really fast, you'd hit this flat spot and take off, and you could get lots of air time. Maybe that's what the landings are for. You can get air, especially on when you're leaving the building. You pick up some real speed and just take off and land right around here somewhere. Maybe that's what they're for. So it would take 3 ramps and 2 landings. I think that's what they asked, isn't it? Yeah. Now, this last section here, part C, what is the total length of the base of the system of ramps? In other words, what they want to know is this whole thing. And they're referring to if we actually constructed a system of ramps for part B, where it's actually 7.5 over here, 7.5 feet, where there would be 3 of these and 2 of these. So it's really kind of simple. There's only one thing I would point out. We found that the length of this base is 29 feet, rounded off to the nearest foot. And it's going to be the same for each one. This is 29 feet. I mean, that's how mathematics works. This is 5 inches, pardon me, this is 5 degrees, this is 30 inches, this is 29 feet. If this is 5 degrees and this is 30 inches, this has to be exactly the same as this. So, with 3 ramps and 2 landings, what we need is 3 of these 28.51 bases. That's this base here. So, give myself a little more room here. And so we can write that the total base is going to be 3 times 28 point, I think it was 57. I can't read my own writing most of the time. And to that, we have to add, well, there's no angles involved here. If this is 60 inches, this is 60 inches. Because this is the ground, and the ground is considered horizontal. And this has to be horizontal because that's the whole point. It's like a resting spot, I guess, or a launching spot if you're going that way. So 2 times 60 inches. You know, in this case, we got feet here. If we're going to add these up, adding inches and feet just does not make sense. So let's convert 60 inches to foot. What happens if we convert 60 inches to feet? If you divide 60 by 12, I would get 5. I think everyone else would too. So that's 5 feet. And what does that turn out to be? And before I go any farther, let me point out that there's a mistake down here. Yes, it is 5 feet, but there are 2 landings, not just 1. So this has to get multiplied by 2. Now, oops, I lost it. What's 3 times 28.57? 3 times the 28.57, let's say roughly 85.7, and 2 times 5, of course, is 10. And that's 95.7 is 85 and 10, and they want it probably to the nearest foot like last time. And that would be 96. Oh, and this was supposed to be 29 here. Pardon me, this is 29. This was the answer to part B. Sorry. This one was 29 and this one was 96. Well, here's one where I think they tried to drive you nuts by giving you information you probably don't need. They say the base of the cone has a circumference of 80 feet. Well, we haven't even studied any of the formulas involving circles. And circumference, if you don't know, is the distance around a circle, as opposed to perimeter, which is the distance around the polygon. Well, so, with the information given, they'd like us to find h, this right here, and s. Well, that was embarrassing. I got that wrong. We are going to use the circumference. We do have one formula for circles. It's several chapters from now. We're going to study many formulas involving circles, but we already have one for the circumference. I think that's probably the only one we have talked about so far in this class, and didn't use it much, but if you remember, the circumference c equals 2 pi r. And I guess we're supposed to know that. We used it once. And that means we can use that to find out the radius. And that's the problem here. We have the angle, but we need some dimensions here. We got to know this side, or pardon me, this leg, or the hypotenuse here. We have to know something, because just plain 32 degrees doesn't cut it. After all, 32 degrees applies to this, but if I cut it right here, it would still be 32 degrees, and I still wouldn't know anything. I could extend these out to here and have another line that this line could extend out here, and then h would be this. It'd still be 32 degrees, but I have to know something about one of these sides. We don't need to know a lot, but we have to know something. In this case, we can find r, and r would be the distance from the center to the circumference. And we know that this equals 80, so r is just going to be 80 over 2 pi. So if we make use of that relationship, we get that that's supposed to be a 1 there. That's r is 12.73. This would be r here. Well, now we've got something, because we've got that the tangent of 32 degrees is going to be opposite over adjacent, h over this, which we just figured out is, call it 12.7, I guess. So h is going to be 12.7 times the tangent of 32 degrees. And what might that be? 0.625. So we plug these into our calculator, and we get 8 for h over here. Okay. And we've already got 12.7 for this one. They want to know what s is. Well, I think we're just going to have to use Pythagoras' theorem for that. Our tangent function doesn't tell us anything about the ratios of the sides and the hypotenuse. But we will. In upcoming chapters, there are a couple of functions which tell us all about the ratios of legs to hypotenuses, or hypoteni. Or there's a hypotenuse. Look, there's another one. For now, I think we're just going to have to use the Pythagoras theorem. So we can write 8 squared plus 12.7 squared s squared. Well, if I square these numbers, I get this over here, add them up, I get 225.3. That's s squared. So s is going to be the square root of this, and that's 15, isn't it? Well, roughly. I mean, I guess I should put the squiggly approximately 15 feet there. So if this, what we had to do was think back to, like, what was it, the first or second week of this class, when we pointed out the formula for the circumference. We used that to find r. And we just treat this like it's the radius, even though it's on the outside of the circle. That's okay. It's the distance from this center to the circumference right here. So that works. This is not the curved distance. I mean, if this thing were following the actual circle, if like an overhead view would be like this, right? Well, if this line here followed this curve rather than just going straight from here to here, well, that would be a complete mess. But that's not what they mean when they're drawing this line here. So what they mean is this straight distance from the outside of circumference to the edge there. Well, hope you had as much fun as I did. That's about it.